Alright, so recall that in the last class we learned what was called the RREF. We have not yet been able to give an algorithm for that. So in this class we will give an algorithm for that, and what we will see is that it has lots and lots of application as per the understanding of system of linear equations is concerned. So let us do what is called, so what we had learned when solving a system of equation was the Gauss elimination method. We had learned this Gauss elimination method. And what was that Gauss elimination method? You had the matrix, you took the first one entry here which was a non-zero entry, used it to make every entry here to be 0. So we made everything 0 here, alright. That was the thing we did. The next thing, we looked at the second entry, so we forgot about the first row and first column. Then we came to the 2 entry of the new matrix. If this entry was non-zero, we took this as a pivot and made everything 0, fine. If it turns out that this entry is 0, we can interchange two rows and then get a pivot and then proceed. All right, that was the idea of Gauss elimination method. But at each stage we just moved down. From the first row we went to the second row to third row, third to fourth, and so on. All right. So we just went down, first to the second, second to third, third to fourth, and so on till the mth row. This is the way we proceeded. All right. And in the process we also looked at second column, third column, and so on. Fine. Now we would like to know what is called Gauss-Jordan method. We want to understand what is called Gauss-Jordan method. All right. So Gauss elimination method gave us the REF, row echelon form. All right. Now this method, Gauss-Jordan method, is going to give us the row reduced echelon form. All right. So therefore we need to be careful. So let me write the actual, without doing any mistake, the algorithm. So algorithm is, so I have a matrix A which is given to be a matrix which has, so maybe m cross n with real entries or complex entries, what it is. So A is a m cross n matrix with real entries. Fine. So the first thing is our input is A, and what will be the output? Output will be RREF of A. So whatever we get, final output will be the RREF of A. It will have all the properties of being RREF. All right. So this is the input. The first step that we are going to look, or second step, whatever you want to say, is the A itself. A is itself the region for us. Now what is this region? Region means the place where I am going to work on. So for me initially it is the whole matrix which is the region for me, the whole matrix. All right. Whole matrix is the region. All right. Now what do I do? Third, if all entries in the region, or which is same as the A, all entries in A are 0, stop, and this is the RREF. This is the RREF. All right. So we stop if all the entries become 0 for us. All right. Fine. Else else find the leftmost non-zero column. So, you are looking at the column, the first column, second column and so on, and find its topmost non-zero entry. All right. So, what we do is that if the matrix has all entries 0, we stop, we have the RREF. If it is not, else you can find the leftmost column, all right, which has a non-zero entry. In that column which has a non-zero entry, pick the topmost non-zero entry. That entry is our pivot. Find its topmost non-zero entry. This is our pivot. This is our pivot. All right. Make this pivot 1. Make it 1 by dividing by the number whatever it is, by dividing the required number. All right. So, what you are doing? We have non-zero entry. This has become a pivot. We have also made it 1. Now, put it as, or interchange this with the first row. So, interchange so make this the first. So, make this row as our first row, use it to make every other entry in that column as 0. All right. So, what we have done? I had look at this part, maybe the first column consists of all zeros. All right. So, first column is all 0. So, you do not worry about it. It turns out that suppose that the second column I have a non-zero entry here, all these entries are 0. So, what do we do? First, this is the pivot that I have. I multiply it by the number, put it back. So, what I get now is a matrix which has 0 here. Now, there is a 1 here and I do not know what they are, some entries are there. I use this one to make every other entry 0 now. Is that okay? Once I have done that, I forget about this part and this part. All right. At the next stage, that is at stage 4, all right, step 4, what we are going to have is that this becomes our new region. All right. So, here we need to work on it. Is that okay? So, we go back to step 2 with this as our region and then do the algorithm again and again. Fine. That is what the algorithm is about. So, let us take an example to understand it better. So, example. So, our matrix A is example. A is 0, 2, 3, 7, 1, 1, 1, 1, 1, 3, 4, 8, 0, 0, 0, 1. I have this with me. Fine. So, at present what we see here is that this has non-zero entry. So, the region is whole of A and the first non-zero entry here for us is this. So, this is the pivot that we are going to look at. So, what we are supposed to do at the next stage is, so do not write A here because now the matrix is going to change. So, it is going to look like 1, 1, 1, 1, 0, 2, 3, 7, 1, 3, 4, 8, 0, 0, 0, 1. Fine. So, what we have done exactly is we have interchanged the first and second rows. Fine. At the next stage, I already see that this entry is 0. We need to make this entry 0. So, we just look at what do we need to do? We need to replace the third equation by doing something with the first equation. And what do we do? Fine, this minus this. So, minus 1. Is that okay? Which is same thing as looking at, if I, from the matrix point of view, if I look at here, the matrix was 0 1 0 0 1 0 0 0 0 0 1 0 0 0 0 1. This was the matrix, 4 cross 4 matrix on the left. Here I need to do first row, there is no change, so as it is. Second row, there is no change. Third row is minus 1 times the first row. Third row is this, and this is the fourth row that we are looking at. Fine. This gives us the matrix 1 1 1 1 0 2 3 7 0 3 minus 1 is 2, 4 minus 1 is 3, 8 minus 1 is 7, 0 0 0 1. This is the matrix I get. So, now at this stage we have taken care of this part. Fine. So, once you have taken care of this, our new region is now only this part, and we need to implement our algorithm only to this part. Fine. So, here what we see is that there is a 2 here, so we need to divide by 2. All right. So, now we do the transformation, which is the second row is being multiplied by 1 upon 2. So, what I get is 1 1 1 1 0 1 3 by 2 7 by 2 0 2 3 7 0 0 0 1. Fine. At the next stage, oh, I forgot to write the pivots here. This is a pivot for me. This was the pivot. These are the 2 pivots that I have. Fine. Now, I need to use this one to make this entry 0. The next entry is already 0. So, I need to look at the third row is being replaced by, again the third row is being replaced by using the second row, which is 1 here. So, I have to put minus 2 here. Fine. So, it is just 1 as a pivot, 1 1 1 0 1 3 by 2 7 by 2. I am multiplying by 2 and subtracting. So, I get here 0 0 0 0, and the last one remains as it is, which is this. Fine. So, here the matrix is going to be, there is no change in the first row, there is no change in the second row, the third row is being replaced by using the second row minus 2 1 0, and this is what I have. Fine. Now, what I see is that these two, the last row is supposed to be the 0 row. So, this is 0 row, it has to be the last row, and therefore, at this stage this is my region that I am looking at. Fine. And here 1 is here. So, we need to interchange. So, let us do that. So, how do I interchange? So, interchange is interchanging the third and fourth row, which is nothing but 1 0 0 0, no change. Third row there is a change, and there is a change in the fourth row. So, this is the matrix that I am looking at, and the corresponding entry here is 1 1 1 1 0 1 3 by 2 7 by 2 0 0 0 1 and then 0 0 0 0, and this is the pivot that I have. I have interchanged these two. Now, the idea is that I need to make, so this was in some sense our Gauss elimination method in some sense, but making ones here as such. Fine. What we need to do is that we need to make every entry here to be 0 here, 0 here also, sorry, not here, 0 here and 0 here, 0 entry for non pivots. This is what we need to do. All right. So, what do I do? At this stage, let us use another ink. So, I am going to write it at one go now. So, what I am going to do is that I am going to use this one to make this entry 0 and this entry 0. Fine. So, I can multiply by, so I want to make this entry 0, the second row. Second row is being replaced by second row 3. Fine. And look at this is 7 by 2 here. So, I have to look at minus 7 by 2 here, because there is a 1 here. Fine. So, this will give me, this part will be 0. Fine. And I can get this also 0 by looking at E13 of minus 1. Fine. I can do it together basically because every entry here is 0. Fine. So, when I subtract, when I multiply this by 7 by 2 and subtract, nothing happens to the other two entries. Fine. Similarly, when I multiply this by 1 and subtract, this will become 0, but these two entries will remain as it is. Fine. So, therefore, I can do things at one go here itself. So, I can write here 0 0 0 0, 0 0 0 1, 0 1, 3 by 2 0, 1 1 1 0. All right. And not only that, you can also see that if I want to play with this now, I can play and there won't be any change in these zeros now. All right. Fine. So, at this stage, now I can do this. I want to make this entry 0. So, the first row is going to be changed using the second one with a minus sign, and I will get it as 1 0 1 0, 0 1, 3 by 2 0, 0 0 0 1, 0 0 0 0, and these are the pivots that I have. And you can see that these pivots, there are 3 pivots. So, I get 1 0 0, 1 0 0, 0 1 0, and then 0 0 1 here. So, I get I 3 because there were 3 pivots. All right. So, please go through it. Very, very important that the 0 rows are at the bottom. The first non-zero entry are the pivots and they are 1 for us. Fine. And every other entry in that row, in that column is a 0, and because of that we are getting this. So, this is very, very important that because of the condition that every other entry in the pivotal column is 0 implies that we get the requisite identity. Fine. And then we can write it as, so if I write this matrix as R, the final matrix as R, then R is nothing but just apply A was there, on A I applied E12, then after E12 I applied E31 of minus 1, then I applied E2 of half, then I applied E32 of minus 2, then it was E34, then it was E34, then these two you can write it in whatever way you want, E23 of minus 7 by 2, E13 of minus 1, and the last one is E1t of minus 1. Fine. So, I have applied so many elementary transformations, all right, on A to get R. Is that okay? Now, if I look at these elementary matrices, they are product of elementary matrices as such, they are invertible, and we know that product of invertible matrices are invertible. So, what we are saying is, let me rephrase it in the next thing. What we are saying is that we have got this theorem which says that theorem, right, that A is m cross n, let R be equal to RREF of A, then there exists a sequence of elementary matrices, says say E1, E2, Ek, such that R is equal to E1, E2, Ek times A, or we can say here is that either this or this is one. The second thing we can say is that I can take this matrix, define P equal to, let P is equal to E1, E2, Ek, all right. Then R is equal to P times A, and what is P? If I look at this matrix P, it is a product of elementary matrices, all of them are invertible. So, their product is invertible, hence P is also invertible. So, nothing but P inverse is nothing but E1, E2, Ek whole inverse, which is Ek inverse Ek minus 1 inverse, E1 inverse. So, P is also, so what we are saying is that if R is equal to RREF of A, then there exists an invertible matrix P such that R is equal to P times A. All right. So, I will be using this idea again and again, that given a matrix A, if I want to look at the RREF, then that RREF is nothing but P times A for some invertible matrix P. I will not be writing it as product of elementary matrices. I will just say that I have an invertible matrix P, so that P times A is the RREF. Is that okay? That is very important for us, and this also tells me that as a third remark you can say that if you look at this, RREF is nothing but obtained through elementary matrices. So, the matrices A and R are row equivalent. So, what was the definition of row equivalent? Go back to the definition, it says that A and B are row equivalent if I can obtain one from the other by multiplying, by left multiplying, all right, or multiplying on the left by elementary matrices. So, this is what we have got. We have obtained R through multiplying elementary matrices on the left of A, and therefore, the matrix A and R are row equivalent. And the idea is that whenever you have row equivalence, the solution set does not change. I am not proving it, but I am just going to write this as a theorem that consider the system Ax is equal to B if, so consider system this, its augmented matrix is AB, fine. So, if CD is row equivalent to AB, then the system Ax is equal to B and Cx is equal to D have the same solution set. All right, this is very important for us, that whenever I go from one system to another system and the two systems are row equivalent, all right, that is important, row equivalent, that I am applying matrices on the left, I am multiplying on the left by elementary matrices which are invertible matrices, the solution set does not change. Is that okay? Fine. So, as a final thing we would like to state here, and I will use it again in the next class, is what is called that this theorem, which I will not be proving it, which is also very important, that so what happens is, suppose you have matrix A which is in M, which is an M cross N matrix. If you just apply Gauss elimination, or you just write the corresponding REF, if you compute REF of A, then it may happen that we may get different matrices depending on the pivots chosen. So, what we are trying to say here is that if I look at this matrix A, it may happen that I have a pivot in the first row, but if I have the pivot in the first row, there is a huge number, or there is a number which needs to be, whose multiplication may result in lot of fractions, all right. But there could be a row in which there are all ones, as in the previous example. If there are all ones, if I have to subtract things, or add things, it becomes a bit much easier. So, to do our process, we may like to interchange different rows at whatever order we want, and that will result in different types of matrices that I have. So, we may get different row echelon forms for a given matrix A. It turns out that that is not true as far as the RREF is concerned. So, whatever way you compute your RREF of A, whatever way you compute, all right, this matrix is unique. All right. So, in whatever way you compute, whatever you do, this matrix will always be unique, and this is very, very important. We will be using this idea again and again, that the RREF of a matrix, RREF of a matrix is unique. All right. So, keep track of this. This is very important. We will be using it again and again to understand a lot of ideas. All right. So, please note that we will be using this RREF idea again and again. So, keep track of that. Thank you.